using Sn1 reactions and Sn2 reactions separately, but now we're going to learn how to differentiate between a reaction that will go through one mechanism or the other one. In most cases, it will be very easy to know if it's one or the other because we're going to learn to recognize some of the elements that will tell. But there will be some cases where there will be an overlap between the two, or it will be a competition between the two types of mechanisms. So the four elements that we need to look for to be able to tell if a reaction goes via an Sn1 or an Sn2 reaction are the four that you see here. So we have the alkyl halide that can be methyl, primary, secondary, tertiary. We will look for a strong or weak nucleophile, the leaving group that can be good or a bad leaving group, and the solvent that can be protic or aprotic. So let's look at those elements separately. So the most important element to tell if a reaction goes via Sn1 or Sn2 is the substrate. So if we have a substrate such as the methyl right here or the primary, those will always go through an Sn2 reaction. If we have a tertiary, it will always go through an Sn1 reaction because remember, this is too crowded for a nucleophile to simply come and attack. The problem is when we have a secondary that can go either via an Sn2 or an Sn1. And so when we have a secondary one is when we have to look at the other elements. Remember that vinyl and aryl halides, so this is a vinyl halide, and this is an aryl halide. Those will result, so if we form the carbocation such as this, that will not happen because that will result in a carbocation with a plus. So the plus on the carbocation will be on an sp2 hybridized carbon, and that's very unlikely to happen. So remember, these carbocations are not going to form. So when we have a secondary when we have a secondary alkyl halide such as this one, then we have to look at the nucleophile. We can have a good nucleophile, a strong nucleophile such as this one. It's good because it has a negative charge, or we can have a weak one such as water that it could act as a nucleophile, but it's not a great nucleophile because it doesn't have a negative charge. It has lone pairs, so it has electron density, but we don't have a negative charge, so that water is not very reactive. So if we look at the two possibilities, the first one is we have a nucleophile here, the O-, that is going to come and attack the electrophile, and the Br, that is the leaving group, is going to leave. So what happens there is we have an inversion of configuration. If we go through an Sn1 mechanism, because we have a weak nucleophile, so weak nucleophile will go through an Sn1, and a strong nucleophile will go through an Sn2. So a weak nucleophile such as water, what will happen is the Br leaves, giving us the carbocation, and then we can get attack from the top or from the bottom, and that will result in a mixture of the cis and the trans isomer in this case, right? So we will have attack from the top and attack from the bottom. And that's one of the ways that you can tell. If there is inversion of configuration, then that means you go through an Sn2, but if you end up with a mixture, with a racemic mixture, then that means you go through an Sn1. The leaving group also matters. So, but in both cases, it matters for both Sn1 and Sn2. So if you have a good leaving group, it's good for Sn1 and Sn2. And the effect of the solvent, we talk about it extensively in one of the videos. So when we have polar protic solvents such as water, it will favor Sn1 because it will stabilize both the ionic intermediates, so in this case the carbocations. But when we have a polar aprotic solvent, so for example when we have acetone, that will favor Sn2 reactions because the nucleophiles are not solvated. So remember, we have something that looks like Na plus Br minus. So remember that what will happen here is that the lone pairs will interact with the sodium and will leave the Br minus ready to go and attack. When we have a polar protic solvent, the hydrogens in the polar protic solvent will interact with the Br and will make it a bad nucleophile. So in summary, when we have a methyl or a primary alkyl halide, the reaction will go through an Sn2. And that will be favored by strong nucleophiles and polar aprotic solvents because those only interact with my positive cations. When we have a tertiary carbocation, when we have a tertiary alkyl halide, it will go through an Sn1 because it will give us a very stable carbocation, so it's likely to happen. So weak nucleophiles will favor Sn1, and polar protic solvents will also favor Sn1s because polar protic solvent will stabilize both the positive and the negative ions. And when we have a secondary carbocation, then we have to look at the nucleophile, at the solvent. So when we have a secondary alkyl halide is when we're going to have a competition between the two mechanisms. So if we have strong nucleophiles, the reaction will go through Sn2, and when we have weak nucleophiles, the reaction will go through Sn1. And remember that the solvent characteristics that we define here and here still stands for this situation. So a polar protic solvent will favor Sn1 and a polar aprotic solvent will favor Sn2. Remember that one of the ways that you can tell if a reaction goes through Sn1 or Sn2 is by looking at the stereochemistry. So if there is an inversion of stereochemistry, it means that it goes through Sn2. And when we end up with a racemic mixture, that means that we went through a carbocation, and that tells us that we got there through an Sn1 mechanism. The other way you can also tell is, now that you've learned about carbocation rearrangements, when you see that your nucleophile doesn't end up where your living group is. So imagine you are always expected to get your nucleophile right there. But when there is a carbocation rearrangement, then your nucleophile doesn't end up with where your living group is. So whenever you see a sign of a rearrangement, that's a sign that the reaction went through a carbocation.